welcome to section 5.2. I hope today I can make things more concrete and less mysterious than they were last time. So we've got a square matrix A. We want to find the eigenvalues and eigenvectors. To find the eigenvalues, you're going to solve determinant A minus lambda I equals 0. The solutions are the eigenvalues, and you guys can read. So here's an explanation of why solving that equation, which is called the characteristic equation, will give you eigenvalues. Then for each eigenvalue, here's how to find eigenvectors. You're going to solve A minus lambda I x equals 0 for x. That's a matrix equation, so the way you'll solve that is by reducing A minus lambda I augmented with the 0 vector. So let's just jump right into an example. Here I've got a 2 by 2 matrix A. I want to find the characteristic equation and the eigenvalues. So I start with computing A minus lambda I. Here's A, here's lambda I, and this is the subtraction. So at this point, I want to solve determinant A minus lambda I equals 0. So I'm going to put 0 on the left, determinant bars, and put in A minus lambda I. Okay, well that's lambda squared minus 5 lambda plus 6. So my characteristic equation is 0 equals lambda squared minus 5 lambda plus 6. I want that in factored form, so I'm going to write lambda minus 2, lambda minus 3 equals 0. You need the equal 0. Your homework only asks for the characteristic polynomial, which doesn't have the equal 0 part, but I'm going to want the characteristic equation. So our eigenvalues, we can just read off that equation. They're 2 and 3. Okay, how to find a basis for each eigenvalue, and I want a basis without fractions. So I'm going to start with lambda equal 2. The stuff in blue is just mental stuff that you don't have to write down. I'm copying down A minus lambda I, and I'm explaining we have to solve A minus 2I x equals 0. And the way we'll do that is by reducing A minus 2I augmented with 0. So I would want to see the stuff in red. And I went ahead and reduced to reduced echelon form. So I've got two variables. X2 is t, x1 is 1/2 t. So my solutions look like t times 1/2 1. But if I want a basis without fractions, rather than taking t equal to 1, I would take t equal to 2. And my basis would be 1, 2, single vector. You don't even need this part. You could go straight from this to writing down a basis. Okay, for lambda equals 3, we're going to reduce A minus 3I augmented with 0. So it went ahead and did that. And again, just simple computation here. X2 is t, x1 is 1/3 t. So a basis without fractions would be 1, 3. If t is 3, then I can eliminate the fraction. Okay, why don't you pause the video and give this one a shot? All right, hopefully you did that. I'm going to go through the solution fairly quickly. A minus lambda I is the matrix. 5 minus lambda, you're just going to subtract lambda on the main diagonal. 3, 3, 5 minus lambda. So to find the characteristic equation, we're going to solve 0 is the determinant of that matrix. 5 minus lambda, 3, 3, 5 minus lambda, which is lambda squared minus 10 lambda plus 25, and then minus 9, so plus 16. All right, so factored, that's going to be lambda minus 8, lambda minus 2 equals 0. The order you put those factors in really doesn't matter, but our eigenvalues are 2 and 8. Now, I only wanted you to find a basis for lambda equals 2, so for lambda equals 2, we're going to reduce A minus 2I augmented with 0. Now I've got A minus lambda I right here. Just put lambda equal 2 in to get A minus 2I. So that gives us 3, 3, 3, 3, 0, 0, which reduces, I'm just going to skip a couple steps, 1, 1, 0, 0, 0, 0. So x2 is t, and x1 is negative t, and your basis is negative 1, 1, if I let t equal to 1. All right, I've got a big warning here that in essence says you can't row reduce a matrix before you find its eigenvalues. and I have an example here to show you why that's true. I've got a matrix A, and its row equivalent to this matrix B. I did that computation earlier. Now B is triangular, so we can read the eigenvalues right off the main diagonal. They're 1, 1, and 0. For a triangular matrix, eigenvalues are sitting on the main diagonal. The eigenvalues of A will not be 1, 1, and 0. So to find the eigenvalues of A in its unreduced form, I compute the determinant of A minus lambda I, which I have here, and I set it equal to 0. And I started us out, I'm doing cofactor expansion on the middle row. And so that's equal to negative 5 plus lambda. And then I get 1 minus lambda quantity squared minus 1. Let's expand that out. That's negative 5 plus lambda times lambda squared minus 2 lambda. And one more factorization, negative 5 plus lambda. And then you can factor out a lambda, and then I'm left with a lambda minus 2. So the eigenvalues of A are negative 5, 0, and 2. Those are different than the eigenvalues of B. So there's your warning. Here's an example. This is one of your homework problems. Find the characteristic equation of A. You don't have to factor it. And so you're going to do exactly what I did in this example here. You're going to compute the determinant of A minus lambda I. Now, I'm not going to go through the solution of that because that is on the last page. So you should pause the video, do that, check your answer. Let's talk about multiplicities. There are two multiplicities in question. The algebraic multiplicity, which is the multiplicity of lambda as a root in the characteristic equation, and the geometric multiplicity, which is the dimension of the corresponding eigenspace. So that's a little confusing. We're going to do an example, but it can be shown that the GM is always less than or equal to the AM for each lambda. So let's just look at AMs. Suppose I've got a matrix A and its characteristic equation is given here. Let's write down the eigenvalues and their algebraic multiplicities. So the eigenvalues are the roots of that characteristic equation. So 1, 0, and negative 2. The algebraic multiplicity is the exponent over each factor. Here's an exponent 1, you're just not seeing it. So this is 2, 3, 1. To find the geometric multiplicity, you'd need a lot more work. You'd have to go ahead and find the dimension of each corresponding eigenspace, and that would be the geometric multiplicity. We'll do that in another example. So here's an example of finding the AM and the GM. We've got a matrix A, and we want to find K, so the GM of lambda equals 5 is equal to the AM. First, we need to find the AM. So I started us out with A minus lambda I, and that's a triangular matrix, so I can read the determinant of that right off of the main diagonal. So the determinant of A minus lambda I is 5 minus lambda, and there's 2 of those factors, so squared, 3 minus lambda, 1 minus lambda, and I set that equal to 0. Okay, the AM, algebraic multiplicity of lambda equals 5, is the exponent up here, which is 2. So now we want to find, so this is the AM, here's the GM. I want to find K so that the GM is also 2. So the null space of A minus 5A will have dimension 2 if, when I reduce the augmented matrix, A minus 5A augmented with 0, I have 2 free variables. So I went ahead and did that reduction, and I only have to go to echelon form. I can see that from this, X4 and X2 are leading, X1 is free. So in order to get 2 free variables, I'm going to need X3. We need this to be free. So that means K is going to have to be negative 6. Otherwise, I'll have a pivot there, and it won't be a free variable. Okay, so pause the video and try this one. Okay, hopefully you did that. I'll write down A minus lambda I. There's A minus lambda I. That's a lower triangular matrix. So again, the determinant of that matrix is the product of the entries on the main diagonal. So my characteristic equation is going to be, I'm going to mentally compute the determinant of that matrix. That's 3 minus lambda squared, and then 2 minus lambda, And then for that last factor, I'm going to pull out a -1 and put 1 plus lambda, and I set that equal to 0. That is the characteristic equation. So now I can fill in the chart. My roots of that equation are 3, 2, and -1, and the algebraic multiplicities are the exponents. So 2, 1, and 1. All right, and finally, find the geometric multiplicity of lambda equals 3. So what we have to do here is reduce a minus 3i augmented with 0 and count the number of free variables. So we're just going to go to echelon form to do that. We don't have to go to reduced echelon. So there's the matrix a minus 3i augmented with 0. And I'm just going to jump right to the echelon form. So I'm going to skip a step. Okay, so there's my echelon form. I've got pivot, pivot, pivot. So those are all leading variables. I've got one free variable. So the geometric multiplicity is 1. If I were to go ahead and find a basis for the eigenspace, it would have one vector in it. Okay, so similarity, this is the last topic, and we'll talk about this when we talk about diagonalizing matrices. So the definition, A is similar to B if there's an invertible matrix P such that A is PB P inverse. Now similarity goes both ways. If A is similar to B, B is similar to A, so you can just say they're similar. So here's an example about a check for similarity that saves computation. My claim is that A is similar to B, and that's because this equation is true with this as my P. Now I could find P inverse and verify that equation, but it's quicker just to check that AP is PB. Now how to do that, how to get there, if you take this equation here and left multiply by P, you get AP is PB P inverse P, but P inverse P is the identity, so AP is PB. I remember the order by just police shows APB. All right, so let's do that computation. Multiply these two matrices, and we get 2, 3, 2, 6. And then if I do PB, I also get 2, 3, 2, 6. So A and B are similar. Again, we'll talk about that next time, but I'm just going to end with one theorem. If A and B are similar, they have the same eigenvalues. Not necessarily the same eigenvectors, but they have the same eigenvalues and same algebraic multiplicities. Okay, and that is the end of this section.